Just look around you. Our world is absolutely full of shapes. Now, measuring something like a box is easy, right? But what about something with a wild, unpredictable curve? For centuries, this was a huge puzzle. Today, we're going to crack the code and find out how we learn to measure the unmeasurable.
I mean, think about it. Finding the area of a square? Piece of cake. Length times width. A circle? Yeah, we've got a formula for that too. But a shape like this one, it's all curves and weird slopes. There's no simple formula here. And this is the exact kind of problem that stumped some of the most brilliant minds in history. For a long time, trying to find the precise area of a shape bounded by a curve was a massive challenge. But you know what? The solution turned out to be beautifully simple. It's all about just changing how you look at the problem.
So what's the big idea? Well, if you can't measure the whole thing at once, then don't. You just slice it up. Seriously, think of a loaf of bread. You don't try to eat it all in one go, right? You cut it into these nice, manageable slices. We're going to apply that exact same logic to our weird, complex shape.
And what's the simplest shape we can use for our slices? One we all know and love, the humble rectangle. Okay, now this is where the magic really starts to happen.
So let's just take a first guess. We can kind of tuck a few wide rectangles under this curve. Now, it's obviously not perfect. You can see these big gaps where we're missing some of the area, and you can see the corners that stick out over the line. It's a really rough approximation for sure, but hey, it's a start.
Okay, but what if we take that same idea and just take it to the extreme? Instead of a few fat rectangles, imagine using thousands, millions of incredibly thin ones. Now look at that. The gaps? They almost completely disappear. The little bits that stick out get super tiny. The more rectangles we use and the thinner we make them, the closer we get to the actual true area. So let's zoom in on one of these perfect little slices. Mathematicians have a fancy name for it, an infinitesimal slice. But its area is super simple. It's just its height, which is set by the curve, we'll call that y, multiplied by its incredibly tiny width, which we'll call dx. This little y times dx rectangle, that's our fundamental building block.
All right, so we've got the idea. We slice our shape into an infinite number of these perfectly thin rectangles. But how do you add up an infinite number of things? You can't just punch that into a calculator. We need a special tool for a job this big.
And that special tool is called integration. Now, don't let the name scare you off. At its heart, integration is really just a super powerful way of adding a whole bunch of stuff up.
We use this symbol right here. It kind of looks like a stretched out S, and that's on purpose, S for sum. Just think of it like a machine. You feed it your building blocks, those tiny y/dx slices, and you tell it where to start and where to stop. It then does this amazing continuous addition, perfectly summing up all those infinite slices in one single powerful step.
So let's put it all together. Integration is simply the process we use to add up every single one of those tiny rectangular slices from our starting point to our ending point to find the exact, perfect total area underneath the curve. That's it.
Of course, a powerful tool like this comes with a few rules of the road. But don't worry, they're not really traps. They're actually very logical when you think about them.
So what happens if our curve dips below the main horizontal line, what we call the x-axis? Well, the integration tool actually sees that area as being negative. But since we're talking about a physical area, something you can touch, which can't be negative, we have a simple rule. If the calculation comes out negative, we just take its positive value. Easy. Okay, so we've totally mastered finding the area under one curve. But what if we want to find the area that's trapped between two different curves? Well, the logic here is just as elegant.
Believe it or not, the logic is surprisingly simple. First, you use integration to find the entire area under the top curve. Then, you do the exact same thing for the bottom curve. And the final step, you just subtract the bottom area from the top area. What's left over is the exact area that was trapped between them. It's that straightforward.
So you might be sitting there thinking, okay, this is a pretty neat math trick, but what's the point? Why does measuring the area of some weird curvy shape actually matter in the real world? Oh, it matters. This concept is literally everywhere. It's how engineers calculate the lift on an airplane wing. It's how they figure out the stress on a bridge. It's how animators create realistic lighting and shadows in video games, and how economists model financial markets. It is a cornerstone of physics and statistics. This is not some abstract theory. It's the hidden language we use to design and understand our entire modern world. And that right there is the most amazing takeaway.
We started with such a simple, intuitive idea, just slicing a weird shape into a bunch of rectangles. And from that one little idea, we unlocked a tool so powerful it can design, model, and calculate the incredible complexities of the world all around us.
It really makes you think, doesn't it? This ability to measure the unmeasurable has already unlocked so much of our modern science and technology. So the real question becomes, what's next? What new problems, what new designs, and what new worlds are we just now becoming able to calculate and create?